Hi guys, welcome to my channel. Today in this tutorial, we'll learn how to create test bench for the D flip-flop we created in our last lecture. So, as indicated in this test bench that I've already created, I have written the inputs here as clock. The input should be a register, or all inputs should be a register, enable input, and this is reset input, and this is the 4-bit D bus. Output should be a wire, which I have indicated like wire like this, and output is 4-bit wire. Variable name is Q, and here I have instantiated the unit under test UUT. I have provided the clock signal using the dot operator. So when we use this dot operator, we directly assign the clock variable input to out. And however, we can also write it like this. If arguments are in correct place, if you write the dot operator, it will not consider the argument in correct place, but it will map it to the clock signal accordingly. So it will be mapped properly. And you need not like worry if your argument is first or second. It will be mapped properly. But if you're not mentioning dot like this, then write the number of inputs as per the number of outputs of this unit under test. And after that, after instantiated, we generate a clock signal. Uh, Generate a clock signal outside the initial begin statement of a test bench. Okay, so you will need to like generate a clock signal before the initial begin statement, so that this always statement runs in parallel. And as you know, like whenever you're writing an always statement, the variable inside should be declared as reg. So we have already declared it as reg inside the test bench, so need not to worry about that. The clock is having an off time of 5 nanoseconds and on time of 5 nanoseconds, 50% duty cycle clock signal. And then we write our test bench code. By default, we keep the enable signal as 1. The reset signal is also capped at 0. We do not want to like reset the flip-flop so that output becomes 0. And I'm starting with the 4-bit D input with 000. D will have this value. It will wait for 12 nanoseconds. After that, D will have this value, which is 0001. It will wait for 10 nanoseconds and so on. Yeah, so I have kept the first waiting period as 12 nanoseconds. There is a reason why, because I want this D signal to be in sync with the D flip-flop. Otherwise, there will be an issue with the flip-flop and the outputs will not be shown correctly. Otherwise, it will show like previous output based if you change this value. So 12 nanoseconds I have covered based on the clock will be 0 for first 5 nanoseconds, and then after 5 nanoseconds it will be 1. After that it will be 0 again. So I have started the output with 0. That is the clock will be initially 0. Okay, and when the clock signal becomes 1, it will receive this output 4-bit 0, and then the output will be 4-bit 0 when it receives D is 4 zeros as input. After that, it will follow normal D, G0001 and so on. Let's simulate this test bench. Okay, no syntax error, so we can proceed with simulation. Okay, so our simulation is generated. You see like the output is shown first, Q30, we can like drag it to the bottom just so that it is consistent and we are able to see what is happening. We will drag the D signal close to the clock, and as indicated previously, you can scroll down to decrease the scale here. Okay, yes. So my first input is 0, uh, but there is nothing at the output is not initialized, so Q is 0. Then this is the positive edge of this clock. It sees my input 0, so output will be 0. Then this signal will stay till the positive edge of the clock. Okay, the next positive edge comes at 15 nanoseconds where my input D is 0001. So this output will be 0001. Again, it will stay for 10 nanoseconds like this. Then it will pick this positive edge of the clock signal and see what is the input, which is 0010, and output will be 0010. Similarly, it will wait for again 10 nanoseconds and see the input at the rising edge of the clock, which is 0011, 3 in decimals of course, and output will be 3 in decimals and 0011 in binary. This is how it will continue uh, till the final value, which is 111, and after that I have reset the D input to 0. After resetting the D input to 0, it will be output will be 0 accordingly, and it continues indefinitely. Yeah, so I hope everything is clear how to clear a test bench for the D flip-flop we designed in the previous lecture. And in similar manner, you will need to like create a test bench like this, generate clock before the initial begin system statement, and then write various cases for testing your module for sequential logic. So I hope everything is clear, and let me know if you have any doubts in the comment section.